So in example 2, I showed you the general process of solving one of these application problems for exponential growth or exponential decay problems. So the first thing that we did in example 2 is we talked about the fact that they gave us 3 different pieces of information for 3 different times. Then once we talked about all of that, we plugged into the exponential formula, and then we saw what we can do from there. So it's again going to be the same kind of thing when we're looking at example 3. So we have an initial value. A sub 0 in this case is 10 grams. They tell us that we have originally 10 grams of this radioactive material. So in this problem, they also have to give us 2 more times. So you want to reread the problem as necessary and see if you can figure out the 2 different times that they have told you. Now, one of those times is relatively straightforward. They ask us for the amount of radioactive material at a t-value of 50. I'm going to put that as my 3rd time. So we have time equals 0 up here, we have time equals 50 down here, and they're asking us for the a value associated with that. So I'm saying then that the problem gives us 1 more time. And they give it to us in a slightly different way than they've done it in examples 1 and 2. This time they told us something about an idea called half-life. So half-life is an amount of time. So they told us that we have a half-life of 1,690 years. So that's our time, 1,690. So we have A of 1,690. Now, the comment that I made was that this is called the half-life. So I'm going to make that comment here. This is the half-life of this particular element. Well, the half-life, as you would assume from the name, is that it tells you something about the idea of half. And in particular, it tells you how much time has to elapse before half of your material is no longer radioactive. So we started with 10 grams of radioactive material, but if we have gone through a half-life time span, that means then that half of our material is no longer radioactive. So how much is still radioactive? The other half, 5 grams. So now that we know that then, we actually have a good starting point similar to what we had in example 2. We have an initial value, we have an idea of a particular number that is plugged in for a time, and then the associated a value that goes with that, and then we have a t that's asked to find an answer for. So let's go ahead and see what we see. So we have our general formula again, and again our a sub 0, our initial amount, is 10, so I can just plug that in. A of t is equal to 10 e to the kt. Now that I have that then, I can go ahead and use this idea from my second line to figure out my k value. So once again, I know a of 1690. Now, as you look at that a of 1690, again, I have 2 different ways of playing with that. I can think about it in terms of the function itself. So let's start with that. A of 1690, I'm going to plug in a t value of 1690. So this is going to be 10 times e to the k t. T is 1690. But once again, I also know from my table that a of 1690 has to equal the number 5. So we now have an equation that I can solve for k. And just like we saw in example 2, the first thing that I want to do is get that exponential expression alone. So to get that e guy all by himself, I need to divide both sides by 10. So if I divide both sides by 10, I'm going to have e to the 1690k is equal to 5 divided by 10. Well, 5 divided by 10 is just 1/2. Once again, as I look at this then, I know then that I can take this exponential equation and write an equivalent logarithmic equation. I can change this into a natural log, and it's going to be the natural log of 1/2 is equal to 1690k. Divide both sides by 1690, and I know that k is going to be then the natural log of 1/2 divided by 1690. Let's go ahead and plug that in then. So my a of t in general is going to be 10 e to the k, and that is natural log of 1/2 divided by 1,690 times our t. So there's our times t. There's the formula that I can use for this particular problem. So once again, you'll notice that I haven't rounded the k yet. When I plug stuff in, that's when I'm going to go ahead and talk about what's going to be happening with my k. So on this problem, they're asking me to find what happens when my t value is 50. So, okay, let's do it. We're going to have a of 50 then is going to equal 10e to the natural log of 1/2, all divided by 1690 times 50. At this point, it's just a matter of typing into your calculator again. And again, personally, I would go ahead and do the exponent first, take e to that power, and then multiply that times 10. I'm going to write down the answer on this one, and you can check to see if you can get the same answer. So on this one then, we're going to find that it's going to be an answer that's going to be a little bit smaller than 10. Now this time, I'm not talking about people, I'm not talking about rabbits, so I'm perfectly fine having decimal answers for the number of grams of a radioactive element. So in this kind of case, if you're going to go decimal, you have to decide how to round, and again, it's a matter of reading the directions and doing what the author asks. So in general, the author likes to go ahead and round to 3 decimal places, so let's go ahead and do that. But again, make sure you're reading the problem and doing what he requests. If he asks you to round to 2, round to 2. If he asks you to round to 1, go ahead and round to 1. So let's go ahead and round to 3 decimal places. So if I round to 3 decimal places, I'm going to get 9.797. Now, one more time, if this is not the number that you're getting on your calculator, more likely than not, what's happening is you're trying to round too soon. Leave all of those digits on your calculator screen, and you'll always get an answer that MyLab Math will be happy with. So if you're not getting 9.797, try again. Make sure you leave all of the digits on your calculator screen, and then make sure that you can get this. Now, because this is an application problem, we need to put some units on it. This is going to be grams again. So I'm going to go ahead and write down grams. So after 50 years, we're only going to have 9.797 grams of this radioactive element.